So what we're going to look at here in this mini lecture is something called the TwoSample Ttest. So the TwoSample Ttest is a test that we use when we're making a comparison that's going to be a categorical to quantitative comparison. That is that our explanatory variable is categorical and our response variable is quantitative. So when do we use this TwoSample means test? One, when we are comparing the same quantitative variable from two different and non-related groups. So for example, an experiment with a placebo and a treatment group. Or two, determining if the value for a specific variable is different for men or women, dogs or cats, or any kind of real comparison. Now notice, one thing to notice is that we're only looking at two different groups, the placebo and the treatment group, okay, or dogs and cats, or men and women, okay? So one of the key things that we get about the TwoSample means tests, in this case our t-test, is that it's going to be a comparison between two groups, two and only two. We'll have a different one for doing more than two groups. That's going to be the ANOVA. Secondly, what we need to get here is that it's a quantitative variable. And so all these are quantitative tests, but a quantitative variable is one that can be measured. So for example, maybe we want to see the heights of men and women, right? That's our quantitative variable. Or maybe we want to see the range of motion for stroke patients depending upon the kind of stroke. So maybe one is a hemorrhagic stroke and the other one would be a different kind of stroke. Okay, so what we get here is that it's comparison of two, and specifically it's comparison of two quantitative variables. Okay, so let's take a look at an example. Suppose we wanted to know if bed rails reduce the number of falls that a person over 65 will have during a 3-month period at a skilled nursing facility. In order to test this, you select two random samples from two different facilities, one with bed rails and one without bed rails, and count the number of reported falls from the month of September through the end of November. You want to test this fact with a significance level of 0.01. All right, so we've got a couple of things that we want to notice here. One, you're going to test two random samples from two different facilities, one with bed rails and one without bed rails. So those are our two our categorical variables, right? We have group one is the group with bed rails, and group two is the group without bed rails. Then our comparison, our response variable, so here's our explanatory, the presence of bed rails, and then our response variable is going to be the number of reported falls. And notice that that one's quantitative. So here's our categorical, here's our quantitative. We have the right number of groups, two groups. And so consequently, in this case, we're going to use a TwoSample Ttest. Okay, great. Now, I'm going to go in here, and what I'm going to do is I'm going to examine my data. So I've developed a data set for this particular question. Okay, I'm going to go into Statcrunch. This is my bed rails example. And I'm going to go in, and what I'm first going to do is I'm going to look at a box plot. Now this is a categorical to a quantitative comparison, so hence that's why we're going to use the box plot. So I'm going to click box plot. Column 1, no bed rails. Column 2, with the bed rails. Okay. And then I'm going to put in, I'm not going to put in any markers. When we actually see these inside of the research, they're not going to have a mean marker or a median marker. Okay, my x-axis label is going to be bed rails, so whether or not they have them or not, because that's my explanatory variable, and my response variable is number of falls. Then this will be box plot of number of falls. Okay, we'll compute. All right. Then I'm going to go in, and so you'll notice I generated a box plot, and now I'm going to go in, I'm going to copy, and you'll see there's a little piece of information down here. Okay, make sure that you follow the directions there. I'll click on copy image. And then I'm going to go in here. Okay. And I'm going to click on, I'm going to Control-Alt-V to paste. Actually, it turns out we can just utilize the picture one by right-clicking. All right, and so there's my box plot. All right, so let's take a look here. So using a box plot to analyze our question, we're going to use the box plot to preliminarily analyze the question that we're asking. And the box on the box plot, it's going to represent the middle 50% of our data. And the midline of the boxes is the median of the data set. If the two boxes do not overlap, then there's most likely going to be a difference. So when I go in here, and so notice this is actually our preliminary. This is going to be especially true when we do ANOVA, but it's also pretty much true when we do a t-test. Okay? It doesn't mean if there is an overlap that we won't see a difference. It just means that if there's no overlap, then we will see a difference. All right, so now I look at this, and now I'm looking and I'm saying, okay, well, I've got my one with bed rails right here. Okay, there's its median. And here's its middle 50%. So that's the 25th percentile to the 75th percentile. Then the one with no bed rails, well, whenever I see a box that doesn't have a midline, it means either the median is here, okay, or it means the median is here. All right? So it's either at the very bottom or it's at the very top. We can actually do some investigation, which we'll do in just a minute, to see which statistic it is. But here's its middle 50%. Again, that's the 25th to the 75th percentile. Now, when I go in and I look at this and I say, okay, well, which one actually has the higher incidence of falls? Well, the one with bed rails, okay, you could see has a bigger percentage, right? At least 25% of the ones without falls, and then actually this this other portion here down below, right, is in the area of one or fewer, okay? One or fewer falls. But then when we look at the no bed rails one, what we get is we've got 75%. So this is this portion right here, okay? Right? That's the middle, 25 to 50, 25 to 75, and then 75, this portion right here is the top 25%. So that's like up to, here's 100% of the data, okay? You can see that actually, that number of falls is somewhat higher than the lowest 50% for the bed rails group, okay? Well, this one's actually kind of a little bit harder to see, but what you can kind of tell is that at least on preliminary inspection, the no bed rails group seems to fall more often. So that's important. So it seems that the no bed rails group seems to fall more often, okay, on our inspection. Again, we've got the median here, and the median is either here or here, and we'll see that in just a second. But what you can kind of tell is either the median is at exactly the same point for the bed rails group, or it is actually less than for the bed rails group, okay? All right, great. So there's our preliminary inspection. We kind of looked at it and said, oh, well, it kind of looks like it. It's not great evidence, by the way. This is not fantastic evidence, but it leads us in a direction to say that the bed rails are effective. Okay, now conditions to run the test. Now, anytime we're running any kind of test, we have to actually determine the conditions to run the test. Most of the time, this is a sample size consideration and also a simple random sample to make sure that we don't have any bias. In the case of the t-test, that's basically what it is. Now, it turns out that if the population for the variable, in this case, number of falls, is normally distributed, then we can even do this with small size samples, okay? Although the smaller the sample, again, as we've talked about quite a lot inside of class, the less likely it is that you're going to get a result, okay? So we don't want tiny samples. Or if we add up, and this is N1 and N2, and remember, N is the sample size. So we have N1 and N2, the two samples. If they add up to greater than 30, then we should have the conditions met, or the samples do not deviate significantly from normality. So let's actually, before we look at n1 plus n2 is greater than or equal to 30, right? Let's look at this last one. The samples do not differ significantly from normality. So I go in, and I'm going to, I'll click out of this. I'll click out of my box plot because I don't want to use that for this. What I'm going to do is I'm going to go again to my graphs, and this time I'm going to run a histogram. Okay? And the histogram, I'm going to have both of these. I'm going to create 2 histograms. We'll make a frequency one. It's just fine. My bins, if you remember the start at, it's going to start at 0 because we have a lot of zeros in our data set. And my width in this case, because, right, we're talking about number of falls, a good width is probably 1. Basically meaning that each box that I get in the histogram is going to represent a difference of 1. Okay? All right. Let me actually put in my median bar. Because remember, if you looked at the box plot, we couldn't really tell where the median was. My x-axis label is going to be number of falls. And then my y-axis is going to be frequency, because this is a histogram. All right? Histogram of number of falls. By bed rails. So that tells us what our comparison is going to be. All right. And then we're going to go and we're going to group by. Actually, don't worry about that. So I went in, I selected the columns that I wanted to create the histogram out of. I selected a start at for my bins and a width. In this case, it made sense to use a width of 1 because there's the number of falls, which does not go up very high. And then I'm going to go in and compute. Okay. All right. So this first group, this is group 1, and this is the no bed rails group. And so if I look at it, you'll notice actually in this case, I have a bit of an outlier over here at 8. All right. And that outlier is going to end up skewing things if you remember from your statistics class. And so consequently, this doesn't look like it's necessarily a normal distribution graph. Okay. So consequently, if I didn't have like the appropriate number, I probably would have a problem utilizing this data. Over here, same thing, right? This one actually is what we call skewed right? If you remember, this is skewed right. And so what we have here is we also have a distribution that does not look normal at all. So consequently, in both cases, for both of our histograms, it appears to me that I probably want to make sure that I have some of the other relationships covered. Okay, so if I look here, I can't utilize that one. Doesn't work for the sample size is not differing significantly from normality. The second one, the population for the variable is normally distributed. Well, in general, as a researcher, you'd either know that, or like in the case of this class for like an exam or something like that, I'd tell you. So we'd go up here and we'd say, suppose we wanted to know if the bed rails reduce the number of falls, right? You might go through and say, hey, is there anywhere in here where they tell me that the number of falls is normally distributed? Okay, by the way, notice that I'm looking at the response variable here. And the answer is no. There's no way, it doesn't tell me that it's normally distributed. There's no reason to believe that it's normally distributed, especially because my samples don't look normal. So this one, no. Okay, no, not that either. Okay, not that one either. Well, what can we do now? Well, I guess I'm going to have to look at the sample sizes now. N1 plus N2 is greater than or equal to 30. So I go back into my data set, look here, okay, and I notice the no bed rails group has, oh, look at that. It's got 42 elements in the no bed rails group, and there's 46 in the bed rails group. Okay, so N1, we'll say is 42. N2 was 46. 46 plus 42 equals 88, excuse me, 88, which is greater than or equal to 30. So check, that works. All right, so you've got three places that you can check actually to determine whether or not a distribution actually, a data set can be used in order to run a particular test. Oftentimes with a t-test, what you're really looking at is you're going to look at, do I have a sample size that's big enough? All right, if you remember, this has to do with the central limit theorem, which is something that was talked about quite extensively in your statistics class. And it really allows us to actually be able to utilize the t-distribution. Okay, cool. So there's the check on our requirements. Remember, the population for the variable is normally distributed, or n1 plus n2 is greater than or equal to 30, or the samples do not deviate significantly from normality. Now, a couple other things here. You do not need all of them. You only need one of them. But you also need a simple random sample. So there you are. All right, now let's talk about the t-distribution. The t-distribution is used very specifically for these kinds of tests. They're tests for means, okay? And we use them when we lack the standard deviation for the population of falls, in this case, in the skilled nursing facility. If we had that standard deviation, we could use, right, if we had this, you could use the z-distribution, or the normal. In reality, that never happens when we're doing a two-sample t. We never have that difference. We never have that standard deviation, and so consequently, we're always using this t-test, the two-sample t. Okay? So, what do we need? Well, we're going to need, we'll make a determination of the degrees of freedom. This is going to end up being n1 actually plus n2 minus 1. All right, so that's, in that case, it's going to be 88 minus 1. And that has to do with the fact that because we lack that standard deviation or those standard deviations, that we can't actually, we have to account for that in terms of our sample sizes. It's a little bit beyond the scope of this class. And so that ends up being 87. And we end up with this t-distribution. Okay. All right. Okay. So now that I know this is going to be my distribution, okay, and I'm going to be looking at, to kind of give you an idea, we'll talk about this in just a second. This t-distribution is we're going to compare against no difference. So, yeah, you know what? I'll talk about that in just a minute. All right. Now, like any other hypothesis test, we're going to have a null hypothesis, and we're going to have an alternative hypothesis. All right. So we're first going to look at and establish the two groups that we're looking at. So group 1, we're going to say, is the number of falls for the no bed rails facility. And you always have to declare which group you're looking at and which group is which. If you don't, this becomes really confusing for the person who's reading your tests and interpreting your tests. And in addition to that, it becomes confusing for you when you're running them, because we make determinations based with regards to which tail of the hypothesis test we're going to use based upon which group that we're going to use, which group is which. Okay, so if we switch and make the number of falls for the bed rails facility 1 and the number of falls for the no bed rails facility 2, we end up with a different tailed test. Okay, so now the null hypothesis. All right, the null hypothesis for a two-sample t-test is always going to be mu1. By the way, we should state this is, again, just as a reminder, this is the mean for the population versus an x bar, which is the mean for our sample. So we have mu1 equals mu2, all right? And that's just stating that the two groups have equal means. So if we were going to go in and compare the number of falls for group 1, which is the no bed rails group, and group 2, which is the bed rails group, that actually tells me that they have the same number of falls, okay? My H naught is also can be retranslated utilizing just a little bit of basic algebra, is mu1 minus mu2 equals 0. So let me just show you that. Mu1 equals mu2. Subtract mu2 from both sides. And that gives me mu1 minus mu2 is equal to 0. Okay? Oftentimes you're going to see in the literature this one rather than this one right here. Okay? And that's because what we're frequently talking about is that there is no difference, zero difference, versus there may be a difference, or we might know what there is we might have a hypothesized difference already. Okay, so you're oftentimes going to see this alternative way of writing the null hypothesis. All right, here's our alternative hypothesis. We can have one of three. Mu1 does not equal mu2, which, by the way, would be mu1 minus mu2 does not equal 0. Okay, that is when we do not have a hypothesized direction for our difference. In our example, we actually believe that the bed rails will improve and decrease the number of falls. So what we think that mu1 is going to be greater than mu2, okay? Because, right, mu1 is the no bed rails group and mu2 is the bed rails group. So we actually think that this one is ours. But if we didn't have an idea, if we thought to ourselves, well, I don't know what bed rails do, right? Or there's no reason for me to believe that bed rails will improve it or not improve it in any given way, then I would use the not equal to. We have the less than, okay, which we already talked about. That's not the one for our particular example. And then we have the greater than. So in this case, when we look at this, and this is going to be important for Statcrunch too, we've got mu1 minus mu2 is going to be greater than 0, okay? That is because we believe that the average, right, the average for the no bed rails group is going to be higher than the average number of falls for the bed rails group, okay? And so that's mu1 minus mu2 is going to be greater than 0. Okay, and again, the choice of the alternative hypothesis is going to be dependent on what we believe that our claim is as a researcher. Okay, so now let's go into Statcrunch and let's actually run this. I'm going to go in. Here's my bed rails one, and I'm going to go to stat, then tstats. Now this is a two-sample test. Remember, that's how we started out. We said, okay, I'm going to look at a two-sample test. I'm going to do this with data, because that's what I have. My values, column 1, remember column 1 is the no bed rails group, okay? Now, be careful. It doesn't always line up that your data set looks exactly like your null and alternative hypothesis. It just happens that that's the way it is in our case. Then column 2 is going to be our bed rails group, all right? Okay. We will not be pooling variances, all right? And we have h naught mu1 minus mu2 is equal to 0. That's fine. And our alternative, remember what we said? It's going to be greater than 0. I'm also going to put in this p-value plot, because I think that it might actually be handy for us. And then I'm going to go in and compute. All right. So let me just review what exactly we did. Okay. I went in first to stat. Went down to tstats, TwoSample, and in this case I had data. Sometimes you might actually do it with a summary. Okay, summary means that you're given summary data. Then, once I got into my menu, I went in, I put sample 1, made sure that sample 1, which was my mu1, was in the values in for sample 1, and then sample 2, I made sure that my sample 2 was the same one. Pooled variances, notice that we turned that off. And then I put in my null and my alternative hypothesis. And then I went in and I computed. All right. Now, I'm going to go ahead, copy. You can actually just highlight the whole thing. Copy. All right, this should not be click on pooled variances. This should be click off. So taking that off, click off pooled variances. So here we go. And here's All right, let's take a look at now at this, the two-sample t-hypothesis test. You notice that it has our null and alternative hypothesis written in those alternative forms. It's got my sample difference and my standard error, okay? And then it has a t-stat, and this t-stat, that's the test statistics. So that's t equals 2.808, okay? And so that actually tells me how many standard deviations we are away from no difference. So we're going to look at this in just a second. The bigger t is, the more likely it is that we're going to reject the null hypothesis. And what we're given here is a p-value, and this p is equal to 0.0033. Okay? So that p is the probability that we will attain a higher difference by random chance, okay? So what this is saying is that there's only a 0.3% chance that we'll actually get a higher difference by random chance. That actually means that our difference, the difference that we got, this thing right here, okay, our sample difference, okay, is in fact very rare. By the way, this is going to be x bar 1 minus x bar 2, right? So that's the sample mean for no bed rails, and this is the sample mean for bed rails. The other thing that we want to get about this is that as we're reading this, think about what that means. Okay, so we've got this sample difference that we've got there, and that sample difference tells me that there's almost one fewer fall for the group with bed rails than the group without bed rails. Almost one fewer, right? In some cases, that 0.76 is meaningless. Like if it's like, you know, salary, for example, how much money a person makes in a year. 76 cents is nothing. That's not a difference at all. But in this case, we're talking about almost one fewer fall, right? Fall, and that's a significant difference. So what we want to say is like, oh, that's pretty big. And that plays out here because our p-value is very small and our t-value is actually quite extreme, okay? So consequently, what I'm looking at here is that I'm going to end up rejecting the null hypothesis because I got a big difference in terms of the kind of thing that I'm actually studying, the number of falls. All right, now let's take a look. There was another thing that actually got pulled out of here. Okay, and if you remember, I did a p-value plot, and that's what this thing is. So I'm going to copy. Let's take this. All right, now what this is my t-stat, and it's got a degrees of freedom of 66.67, which is, well, it is, it's a different calculation for the degrees of freedom. So don't worry too much about that. You just know that we've got to calculate degrees of freedom, but Statcrunch ends up doing it for you, okay? And what I get here, I got my p-value, so the area here under the curve, that's 0.0033. And if you remember, my alpha, okay, my alpha was like 0.05. All right, that's the area that we have to beat. We clearly did, right? We clearly did here, okay? And in fact, this thing here, that value, which is my difference, that's x bar 1 minus x bar 2 equals 0.76. That's where that's located, and that has a t-value equal to 2.8, is really extreme, okay? That's what that's saying. So what we got, like just we talked about when we did chi-squared and what you've seen before when you've done single sample hypothesis tests, is this, right, really far away from the mean. That's pretty significant, right? And by the way, notice here, this has a mean of 0. The reason why is that is your null hypothesis. That's mu1 minus mu2 equals 0. That's no difference, right? No difference. And our difference is very extreme. So again, we have the third way of telling whether or not this is pretty extreme. So one, we look at this difference. We said, oh, x bar 1 minus x bar 2, that's almost 1 whole fall less for the bed rails group. Then we get a t-value. This t-value, that's really extreme. That's 2.8. 2.8 basically standard deviations away from the mean. That's really far away from the mean. And we get a p-value that tells me that getting my difference of 0.76 is actually really rare. There's only a 0.3% chance that I will in fact get a p-value of that size. Finally, I look at my distribution plot, and my distribution plot in fact tells me, right, my alpha value of 0.05 is over here, okay? My t-value is in fact way in that critical region, and my p-value of 0.0033 is much smaller than 0.05, right? So I'm really far away. So what does that tell me? It tells me I'm going to reject the null hypothesis, okay? And so we get our mantra. If p is less than alpha, then we're going to reject the null hypothesis. Okay? In this case, p was equal to 0.0033, and alpha was equal to 0.05. So clearly p is less than alpha, so reject the null. Notice that everything inside of this test tells me that in fact the bed rails, the group with bed rails, in fact performs better in terms of decreasing number of falls, or maybe not decreasing, but they have fewer falls. Okay? And finally, we get to concluding the test. If we reject the null, here's the kind of conclusion we're going to get. There is sufficient evidence to reject the hypothesis that the mean number of falls for the group without bed rails is the same as the group with bed rails. That's the one we're rejecting, right? We're saying, no, they're not the same, right? This is saying not the same. Then we also, because we concluded the test this way, we can also write there's evidence to support the hypothesis that the mean number of falls for the group without bed rails is greater than the group with bed rails. Okay, that is in fact also what we stated. Now, if we had failed to reject, then we would only actually need to say that there is not sufficient evidence to reject the hypothesis, and we wouldn't use the second one. So the second one is only if, right, only if we reject. That actually says, you know what? My alternative as a researcher is in fact correct. Okay. All right. So here's if we fail to reject, there is not sufficient evidence to reject the hypothesis that the mean number of falls for the group without bed rails is the same as the group with bed rails. Okay. Or there is not evidence to support the hypothesis the mean number of falls for the group without bed rails is greater than the group. So you only need one or the other if you in fact fail to reject. Awesome. So that concludes our mini lesson on the t-test for means, right? 1, big thing. This is a C to Q test. That is that your explanatory variable is categorical and your response variable is quantitative. 2, this is for 2 samples. If you have more than 2 samples, right, okay, you're going to utilize, you're going to use an ANOVA. And also, you'll notice there's one other thing. It's not dependent samples. And for us, that's mostly meaning no pre and post test. All we did was we went in, we tested after the fact, so there's no pre and post test, so these are not dependent samples. Then 3, we are comparing our sample difference against no difference. The bigger the difference that we get from the test, the more likely it is that we're going to reject the null hypothesis. Okay, and then finally, and I'm just going to always remind you of this, if p is less than alpha, reject the null. So you're going to always remember that. You just want to remember what is your null hypothesis, and that's going to help you in terms of making your determinations. All right, that concludes.